So for the third application of differential equations, and that is specifically problems that are mathematically modeled using differential equations, we have the mixing process. So in here, we are to visualize a tank which has a mixer. I missed drawing the mixer here to ensure that the contents in the tank at any particular time, at any particular point is uniform. So there has to be a mixer here. And there is a solution entering with rate R sub in and out. The rate going out of the tank is R sub out. So I changed the labeling of the concentration here based on the requirement in our second sample problem, which is K for the concentration. So let's say, for example, the concentration here is K for the fluid that is entering and K for the fluid that is leaving. So notice that I did not anymore place here a subscript out for the concentration of the solution leaving the tank. It's because it's also the same solution that is inside the tank. So the solution concentration inside the tank is the same as that of the solution leaving the tank. Now, I really empathize for the ECE students here who have to listen to this, but this is also written in your CMO, the CHED Memorandum Order for Problem Applications for Differential Equations. So, it's included also in this case in your differential equation. So if we are to present in the form of a differential equation, the amount of, let's say, solute or solid in the tank at any particular time, or the rate in which the amount of any particular solute in the tank at any particular time is changing or accumulating, that would be the dq dt. The rate of change of the amount of Q of the solution inside the tank is equal to the product of the volumetric flow rate, R in, times the concentration C in, minus R out, the volumetric flow rate out of the tank, times the concentration of the contents of the tank, which is the same concentration as that of the fluid leaving the tank, plus this C that you see here, the C sub n, and the C that you see here in our illustration is the K. So K in and K out. So it's just important that whenever you use a different letter or scenario than the one that is appearing in your equation, there's no problem with it as long as you define those particular letters. So in here, in our problem, it's C in and C. Whereas in our equation, rather in our illustration, it's K in and K. So it's all defined here. Q, the amount of solute or solid in the container at any time T. R sub in, the rate at which a certain mixture enters the container. And this is always class, most of the time, 100% of the time, volumetric flow rate, meaning it's volume per unit time. I'm referring to the set units. The C sub in is the concentration of the mixture entering the container. That's the K sub in our illustration. The R sub out is the rate at which a certain mixture flows out of the container. And C, the concentration of the mixture flowing out of the container, or the concentration of the mixture inside the tank. Concentration is C, is the same concentration of the fluid leaving the tank. Now, this solution that is referred here is not the solution of this DE. Because if you notice, the way the DE is written is your unknown variable is Q and the independent variable rather, is time, with the C's here representing concentration. The solution that is referred in here in the box is the solution concentration at any particular time. So if you have a copy of this and you'll have it printed, so you can place here a specific annotation that this is solution concentration at any particular time of the fluid inside the tank. It's not the solution of this problem, because this problem does not have a ready-made solution, unlike the first two sample problems that we have discussed already. This problem can be solved, or this differential equation can be solved depending on the skill of the one who's using it. It can be solved using separation of variables, or it can be solved using linear differential equations only. So it depends on the form of the DE resulting after you have already substituted the values on this formula. So again, I will emphasize this C is the solution concentration of the solution inside the tank at any particular time. So if you're going to look at it, the concentration is amount of solute or solid at that particular time inside the tank is Q, that's Q in there, and it's to be divided by the total volume of the solution inside the tank at that particular time also. The total volume of the solution inside the tank at any particular time is the initial volume. So you can see here the quantity of the mixture in the container at T equal to 0. This quantity Q sub O class is volume quantity, not mass quantity. Now for CHs, they know that if it's volume, it's represented by Q. So in here, you can change this Q sub O to, if you want, to V sub O. So you won't get confused with the Q that is being used in here. The Q sub O again is the volume, the initial volume of the fluid inside the container, or of the liquid inside, or of the mixture inside the container. Now, what is this being added to the initial volume of the fluid inside the container? This is actually the difference of the rate of fluid coming in and the rate of fluid coming out multiplied by the time elapsed. So whatever is the volumetric flow rate coming in, we subtract the volumetric flow rate coming out, and it will be multiplied by T. That would be then the net surplus of liquid that is entering the tank, or the net deficit of the liquid entering the tank, in cases wherein your rate in and your rate out are not equal. If your rate in and your rate out are equal, this term here is 0. So automatically, your concentration inside the tank would simply be the amount in terms of mass divided by the volume of the liquid inside the tank. It doesn't matter whether it's initial volume or volume at any particular time, because the rate in and rate out is equal, or are equal. If they are equal, so then there's no amount of liquid that is added here. In the case wherein the rate coming out is greater than the rate coming in, then at some point your tank will go dry, because what comes in is less than what comes out. In cases wherein R in is greater than R out, there's a time for your tank to overflow, because what goes out is less than what comes in. It will only be constant, I'm referring to the volume of the liquid inside the tank, when this R in and R out are equal. So then you won't have any problem with this second term in the denominator. You will only have mass of the solid or solute divided by the initial volume of the fluid inside the tank, or of the mixture inside the tank. Now, a classmate of yours raised a concern regarding the representations, I mean the letters that are being used in our model DE. You can always change it, as long as when you write your solution, you are defining the letters that you're using, or the variables that you are using. So I will understand. Unless, of course, your solution comes from Mars, wherein I don't understand where you're getting it. And I'm sure you yourselves don't understand as well. Okay? Now, we have this sample problem number 1. It's actually already uploaded with this particular illustration in Canvas. I'd like to solve this differently than the solution that you're seeing here with the explanation, because this comes from, or this came from Sean's outline. So I'd like to explain it the way students would attack this problem if they were the one who are solving it. Okay, so I only have 2 anyway in here. Now, in sample problem number 1, We are given a tank initially containing 40 pounds of salt dissolved in 600 gallons of water. Now, starting at time equal to 0 for this particular tank, water that contains 1/2 pounds of salt per gallon is poured into the tank at the rate of 4 gallons per minute, and the mixture is drained from the tank at the same rate. So for letter A, you are to find a differential equation for the quantity Q of T of salt in the tank at time greater than 0 and solve the equation to determine the Q of T. And letter B, you are to find the Q at T equal to infinity. Now this class, this Q equal to infinity or at T equal to infinity, this is equivalent to saying how much salt will be in the tank after a very long time. So whenever a problem says what is the amount after a very long time, your T then is equal to infinity because that's how it's supposed to be understood when we solve problems already. The phrase after a very long time is infinity. Now, I'd like to solve this problem the way you are trained to solve it. You write down your understanding of the given, what is required, and then the course followed by the solution. So I'm guided by this equation. The rate of accumulation of the amount of salt at any time inside the tank is the difference of the product of the rate coming in and the concentration. So RC in, RC out. That would be my rate of accumulation. So in our problem, it says in the first statement, 40 pounds of salt dissolved in 600 gallons of water. So if you're going to write it down, you have Q sub O, the amount of solid, as 40 pounds, and that is at time T sub O, or time equal to 0, with the volume equal to 600 gallons. That's coming from that statement. Then starting at time T sub O equal to 0, water having this concentration is poured at this rate. So how will we write it down? So you simply write it down that at the same time, wherein this is your condition of the solid inside the tank with the water it was dissolved into, you have this concentration and rate of a aqueous solution of salt entering the tank. So meaning this is the concentration in, which is 1/2 pounds per gallon, and this is the rate, 4 gallons per minute. And it was mentioned that the rate in which it's drained from the tank is the same as the rate that it enters the tank. So I place here R out. So for letter A, you are to determine the Q of T, the expression that will solve for the amount of salt in the tank. Is that the way it's written there? So solve the equation to determine the Q of T, which allows you to determine the amount of salt in the tank at any particular time. However, this one cannot be determined unless you know the differential equation. And letter B, you are asked to determine the Q of infinity. So in our case, if you go back to this formula, you have dq dt is equal to the rate coming in gallons per minute, or volume per unit time, excuse me, is 4, and your concentration is 1/2. Now you have minus, so the rate coming out is also 4, and the concentration is Q, the amount of salt inside the tank at any particular time, divided by 600. Now you may ask me, where did you get this 600, miss? Or rather specifically, the Q over 600. I'd like to go back to that slide, to that particular part in our discussion wherein you have this. The concentration at any particular time inside the tank is equal to Q. That's the Q that you are seeing here, divided by the initial volume plus the difference in the two rates. Rates coming in minus rate coming out multiplied by T. So So that's the way we did it. So your initial volume is 600. It's stated there. You don't see anything here because these two, when you subtract, will simply be a 0. 0 times t is 0. So your denominator here will only have the initial volume. It will not have any these two because these two anyway are equal. So that's the reason why you have Q over 600 for the concentration. Okay, concentration of the mixture inside the tank or of the fluid leaving the tank. So your differential equation in this case, if you're going to look at it, is this one. dq dt is equal to 2 minus q over 150. You take out the 4 here and you will be left with 150 in your 600 if you divide by 4. If you recall my saying, we don't have a ready-made formula for mixing in the case of the differential equation because it depends on the one who's solving it, how he will solve it. This can be solved using linear because I wrote it in the form of linear. I transferred the q over 150 on the left side and the 2 here on the right side. So that makes it linear. And I solved the integrating factor. So 1 over 150 dt, and this is your integrating factor. This is your unknown function q times the integrating factor is equal to your q of x in the linear dE form times the integrating factor. If you will integrate this side, you will have 300 e raised to 0.0067t because 2 divided by 0.0067 is 300 plus c. If you will divide the entire equation by this exponential function, you will have q equal to 300 plus c e raised to negative 0.0067t. Okay? Your q of t is equal to 300 plus c e raised to negative 0.0067t. However, this one is so generic. I say so generic because the C is not known. So whenever you are asked to determine a formula, if possible, if the problem provides you with condition to determine the constant, determine the constant. And we can do that in this case because we know that at time equal to 0, the amount of salt inside the tank is 40 pounds. So if you use that initial condition here, your Q sub O being 40, you substitute in this formula. So 40 is equal to 300 plus C e raised to negative 0.0067 T being 0. This entire expression would be a 1 because anything raised to 0 is 1. So you now can solve for the C, which is negative 260. So the appropriate formula to answer in this case is Q of T being equal to 300 minus 260 e raised to negative 0.0067 t. Now, all you have to do in this formula is substitute the time elapsed and you would know how much of the salt is present inside the tank. That how much is having a unit of pounds. Okay? This is the formula that the problem is asking after you have written the differential equation. Now, I said this would be your ready-made. You cannot rather have the ready-made formula for this because some students may opt to solve this using separation of variables. You can combine the two expressions on the right wherein you have 300 minus q over 350. When that is, if that is the case, your DE is converted into a separable DE. You transfer the 300 minus Q here and the 300 minus Q and the 150 can stay in this side. The 1 over 150 transfer the DT here. That makes it separable. So it really depends on the student on how will this particular DE be solved. It can be solved using separation of variables also. But I'm using linear here. That way you will not forget linear DE because in mixing there are problems which cannot be solved using separation of variables. Meaning the only way that you can handle the DE or evaluate it is using linear differential equations technique. Now, so far we have answered only number 1, and that's the answer here. And you are asked to determine after a very long time how much salt is present in the tank. So you just have to substitute infinity here. So e raised to negative infinity class is always 0. This becomes 0. So after a very long time, there is 300 pounds of salt in the tank left after a very long time, meaning after a very long time. Okay, it could be like 1 day, 1 week, after a very long time, as long as the process continues. So this is in the case of our sample problem number 1. This tank wherein the fluid entering rate is the same as the fluid leaving the tank rate. Okay? Any question before I go to sample problem number 2? The solution is also written here from Shom's. That's the way Shom solved it. Okay, none. So if we'll be disconnected, we will just use the same link. Okay, so I'll read sample problem number 2. A 500-liter tank initially contains 10 grams of salt dissolved in 200 liters of water. Starting at time 0, water that contains 1/4 grams of salt per liter is poured into the tank at the rate of 4 liters per minute, and the mixture is drained from the tank at the rate of 2 liters per minute. Find the differential equation for the quantity Q of T of salt in the tank at the time T prior to the time when the tank overflows. There will be a time for the tank to overflow because the rate coming out of the tank is only 2 liters, but the rate coming in is 4 liters. So it will sometime after some time overflow. And the second requirement is you are to find the concentration K of T. So this time the problem uses a different letter. So if you are not comfortable with the letter or that the problem is using, you can assign your own letter. Then afterwards, just change it to the letter that the problem asks you to represent the unknown. So in this case, it's K of T in grams per liter of the salt in the tank at any such time. Okay. 10 minutes. Okay, now I'll go to the solution of this problem number 2. So our problem number 2 gives us a tank having a capacity of 500 liters. You are to look at this 500 liter value not as the initial volume but rather the capacity of the tank. If you look at it as the initial volume, then everything that you will be doing is wrong. So capacity of the tank is 500 liters, and it says in the problem that these are the values initially for salt and water respectively. So we write it down. Your Q sub O is 10 grams and the volume is 200 liters. If you have 10 grams of salt dissolved in 200 liters of water, then your mass concentration is 0.05, 10 divided by 200. Now, at time equal to 0, the start of the mixing process, this is the initial concentration of the solution that enters at this rate, and this is the rate in which it's leaving the tank. The problem is asking for the Q of T before the tank overflows, meaning a formula that will allow you to solve for the solid content of the salt in the tank. If it's talking about the salt, yes, in the tank before it overflows. And letter B, it's asking for the concentration. So concentration because the unit is grams per liter. The concentration at any particular time as long as the tank hasn't yet overflowed. Okay, so we go to our DE. Our DE, if you recall, you have this. R in, C in, R out, C out. DQ dt on the left. So we will place it here. DQ dt is equal to R in 4, C in 1/4, minus 2. And this time, class, your concentration will be following this guide. This guide. Okay, in the same way that in sample problem 1, it also followed that guide. So your solution concentration at any particular time, this is the rate, by the way, 2 liters per minute. So it's the amount of salt in the tank at that particular time divided by the sum of the initial volume. This is the initial volume, plus the product of the rate coming in minus rate coming out times the time. So in our case, we have Q over 200 plus 4 minus 2 is 2 times T, 2T. If we will simplify this side here, specifically this fraction, this will be Q over 100 plus T. If we divide both the numerator and the denominator by 200. Now, if this is your DE class, this one cannot be solved using separation of variables. This can only be solved using linear differential equations. So you need to transfer this expression on the left side, and one is left on the right side. Your integrating factor mu, or the phi, is e raised to the integral of the q of p of t rather. This is p of t. 1 over 100 plus t. That would be an ln for this integral, and e raised to an ln eliminates the e and the ln, leaving you with the argument of the ln. So this is now your integrating factor. So linear DE based on formula is a known function times the integrating factor equated to the integrating factor times the q of t. In our case, it's 1. So if you will integrate this side as a whole, this would be 100 plus t raised to 2 over 2. Power rule for the entire expression. You can also do that by having 100t plus t squared over 2, but that's difficult. That would make complications because you have an expression here on the left side, which is 100 plus t. So you want to make sure that our expression in association with it is also in the same form. So that is why we have to integrate this side as a whole. 100 plus t quantity squared over 2. At time equal to 0, it's stated in the problem that you have 10 grams of salt present. So we will place there 10 here, and you will have 100 plus 0, so that would be 100. This one would be 100 plus 0 squared, so that would be 1000 divided by 2, so that would be, rather, this is 10,000 divided by 2, so that would be 5,000, and you will have C. So you'll be getting a C value of negative 4,000. So if you want the formula that will solve for the amount of salt in the tank before the tank overflows, that would be Q of T equal to 100 plus T over 2 from here. Why do we have only this one in this side? Because this complicated formula, we divided by the expression 100 plus T. So that eliminates 100 plus T in this side, leaving us with 100 plus T left here over 2. And then this C will have, of course, 100 plus T because we divided our entire equation here by 100 plus T. So this is our equation, and the final workable equation is when you set your C that you got here to negative 4,000. So this is the one that I boxed because the C is already specified. So all you have to do is plug in the time before overflow, and then you will be able to determine the solid content inside the tank, or that's the salt content inside the tank, as long as that particular time is yet not the overflowing time of the tank. Okay? Now, the problem is asking for the K of T, which is concentration at that particular time. So how do we find it? We go back to the basics of chemistry, that concentration is equal to mass over the volume. Our mass at that particular time is this, that the one we got from A. Amuning nakuha tanas value sa A. The mass at any particular time. So when you divide that by the volume, that would be the concentration that is being asked by the problem in grams per liter. So the problem is asking for the concentration in grams per liter. So that should be your guide. What should be the formula for the K of T? So you have Q of T over V. So I copied everything here in the Q of T, copied. And then we divide by the volume at any particular time. The volume at any particular time before overflowing is the initial volume plus the difference of the volume coming in minus the volume coming out times the time elapsed. That's the same volume that we used here in our concentration. This one, 200 plus 2T. Hi? So I have now a 200 plus 2T. If I will factor out the 200, I will have a 100 plus T. So the mathematics in itself takes care of the complexity because I have a 100 plus T here and I have another 100 plus T here. So if I will cancel the 2, that leaves me with 1/2 over 2, and that would be 1/4. And this 4,000 over 100 plus T, if I will divide that by 2 over 100 plus T, this will be 2,000. And this 100 plus T and this 100 plus T will be 100 plus T quantity squared. Now, this is the general formula that was solved for the concentration. This one for the mass of the solid inside the tank. This one is for the concentration of the solid inside the tank before the tank overflows. There will also be problem class wherein the rate coming out is greater than the rate coming in. So then the solution inside the tank, or the tank rather, would go empty after some time. It will go empty because the rate coming out is greater than the rate coming in. Okay? I will be actually disconnected in less than 1 minute. So if you have any questions, you may ask me now. Then we can go back to the link later for more questions regarding the sample problems illustrated. Do you have any question here? Is everything clear on the sample problems?